Morning, Bill.
Good morning. How are things in South Carolina?
Morning, Bill.
Hello. So, how are things in South Carolina?
Pretty warm day, a little bit of moisture, but not much. How about up there?
Yeah, warm here too. It's unseasonable. It seems warmer than it should be for this time of year. But
Ah, Buenos dias, Jesus.
Buenos días, Professor Gale.
yes.
Good morning, everybody. How are you?
Very good. And you?
Okay, thanks. Okay, very good. In these past weeks, I couldn't work in my faculty because there is a strike in there.
Oh no.
Really?
Really. Then I am working since my house this time, but it's okay. It can do.
Well, congratulations on the book that it looks like it is progressing.
Yes,
Memorial book.
it is almost at the final form. Then we are going only to work in the final publication process. Then it is exciting because it was a long work.
Yes.
And then,
But I look forward to it. I'm anxious to see the final result. I think it should be quite an interesting volume.
yes, I think that there is too many works that are very good quality of works, and
Yeah, it's an interesting mixture of subjects,
yes,
which of course was the suitable tribute to the to Dr. Algebraic.
yes, it is because his interest was too broad, then many people was working with him in different subjects.
So now that the book is almost finished, I suppose people will be starting to ask when the next conference will be held.
I suppose. And
Maybe Bill can put it on. Be in charge.
yes.
Yeah.
Maybe not in this moment, but maybe we can talk about this because I think that maybe the next year could be possible, but we need to ask to scientific committee people in the way that we get a successful process. Then, but it's hard work, but I think that it is too much productive and enrich all to us the contact with other people.
Did you have students that are interested in pursuing some of these ideas?
No, I don't ask to them, and I was not working too much in inviting more people to these or seminars, for example. Maybe it is needed to do because young people can be interested in this subject.
Mhm.
Yeah, I'm going to be talking to some people at UTLA, and maybe I can draw some interest from UTLA. I haven't been there for a while because of all the disruptions, but
Yeah.
possibility.
Getting the right scientific committee together, or the public, the administrative committee, it's a critical part, to get people who are motivated to want to do this, to bring it together to a final conference. Even these days, perhaps it's a little bit easier if it's an entirely virtual conference, but still, it does require some dedication. So,
No. But what the conference you said?
I said that that it's important to have a dedicated committee, people who are committed to organizing the conference. I think one reason why our conference was so successful 2 years ago was uh, that everyone was strongly motivated to do it. They wanted to contribute something. So it's hard to know whether or not there will be enough motivation of people to do the same thing again. I'm not sure.
Yeah, we're all getting older is a problem too, of course.
Yes, yeah.
Yeah. Past months, some people was asked to us if we plan to organize a new version of the conference. Then maybe there is some people interested in that.
Yeah. Okay.
Okay.
So today, Jesus, you have something you can sort of present?
Yes, yes. How I said to you before, this is based in one old work that Professor Osiewicz and myself presented in a conference of Mathematica. I am going to present the paper.
Okay.
Wait a moment. I need to localize.
While you do that, I should ask if you received a copy of the paper that which you were the primary author and Oshevich was second author. Um, this was the paper that I was referring to when I talked 2 weeks ago, and Dr. Sobchak asked if I could send it. I found that what I sent was actually a draft of something that was published in a book, and so I didn't have the final preprint of that article.
Okay.
So but I think that the draft that I had was fairly close to the final result, but not identical. So I wasn't sure whether or not you might have like an electronic version of that, actual publication or not.
Yes. Yeah, I didn't have enough time for review the version of the paper that you sent, and But I have the publication in the corresponding proceedings. Then I can send to you. But I'm not sure if I have the LaTeX and PDF version in my computer of the last version that was published, or maybe what I have an order. But if it is not the final version, I can scan the publication and then share with you.
Just for completeness, it's not so critical, but for me it was the starting point for my interest in this sort of Frobenius algebra, and in particular the Frobenius algebra that comes from this subset of the Fröhlicher-Ningenhaus.
Yeah, I'm still interested in those ideas. I'm not sure exactly. I guess a Clifford algebra is an example of a Frobenius algebra, but
yes,
I'm not that familiar with Frobenius algebras.
Well, the critical thing for me was to understand at least something about the coalgebra structure that comes from the Frobenius algebra, and that coalgebra structure is present in Clifford algebra, but not just like in many cases that Oshevich mentioned. This coalgebra structure is present but not exploited. There's no clear applications other than the formal application to the structure of the algebra. So it's a little bit unusual. So because we're looking at mathematics that seem to be critical part of the mathematics, but it has no obvious physical interpretation, So
Yes.
it's like an answer looking for a problem to solve, but not sure what the problem should be,
Yeah, I've been thinking about this idea that I gave you in my talk about compatible nilpotents, and I have some new ideas about it. I wanted to understand how nilpotents are, an algebra of nilpotents might be more general than just a matrix algebra with matrix algebra coefficients. And I have some interesting ideas about that. Maybe if nobody else wants to talk, I could present them in another couple of weeks.
I think that it's interesting to pursue that. On the Frobenius side, the critical thing is how the scalar product is introduced. In addition to the main multiplication that defines the algebra, the Clifford algebra, there is an additional multiplication, that we call scalar multiplication, or in the Frobenius structure, like you introduce that scalar product in a specific way, or maybe I should say in a more general way than what's done when you talk about scalar products in Clifford algebra itself. So I'm not sure, but well, that scalar product is what gives rise ultimately to the coalgebra structure that's part of the overall Frobenius system, right? So
again, I think that the concept of evaluation is important here, because evaluation is a more general product between vectors and covectors, or the
well, but
principle there.
that's critical notion that's in a sense evaluation requires that there be two types of objects, so that you have
Yes.
something that acts like a function and something that acts like values, right? So in the sort of nilpotent algebra structure that Dr. Sobchak is talking about, there is no notion of evaluation yet. Like so you don't use like one part of the one part, nilpotent to evaluate the other nilpotent. At least
Yeah.
I don't see how that happens.
Well, if you just take the sum of these compatible nilpotents, they have square plus one. But if you take the difference of two nilpotents, they have square minus one, which of course is what defines the Clifford algebra structure. But what I've been interested in, if you take three nilpotents that are compatible with each other, what structure do you get? I think I can answer that question now. Or n of them.
This idea of evaluation, though, which is what Jesus just mentioned, makes there being two things sort of more natural, right? So that you think of one nilpotent as evaluating the second nilpotent. But they're of two different characters. Like, so you need some kind of operation that when you apply one nilpotent to the other nilpotent, you get a scalar value, right? You get a
well, certainly the structures are all closely related, but I can see what you're saying. I understand the idea of that's the classical definition of dual space or covectors, or just the dual of vectors.
Yes, directly related to the notion of dual in a classical sense in the linear algebra.
Yeah.
Yes, because I understand this like an operation in where we can assign to a multivector or to one multiform an scalar, an element of scalar. And in this general idea, we need to build the structure of the algebra, starting from the scalar fields. And then in this way, we can, the evaluation operation is natural in this way. And I think that it is important because one way is to include the tensor metric, the metric. But we can get products between forms and, excuse me, between vector forms and scalar forms without using the metric. And then this is more or less powerful, I think, that the idea of a scalar product.
So instead of instead of defining the Clifford algebra, say in terms of a metric, you define it more abstractly, but then introduce this operation, this mapping from multivectors into scalars. So.
Yes, this is the idea, and there is the concept of evaluation.
Okay, I'm interested in what you presented there.
Okay,
you said you Mathematica, so you have some nice pictures, I hope.
Not too much. Not too much, but okay. I'm going to share my screen.
Yes.
Okay. And this is the paper that Professor Osiewicz and I presented in the International Mathematical Symposium. I don't remember if this was in 2004. I think maybe there is there are some electronic publication of this, because it was published with in a formal way, a book of proceedings. Then I think that it is possible to get. But only I presented here, there is the principal ideas here. I can send to you this copy. Maybe now I can, okay, maybe by email I can send to you.
Okay.
But
Okay, please do.
okay. Moment, please. Okay, I sent to you. Many of the concepts that are presented here was included in my presentation. Wait a moment. Okay. I suppose you are seeing my slides now. Yeah. Okay.
Yes.
Okay, this is the title of the work presented in 2004. And this is the abstract that the aims of this was to present an symbolic calculation approach for Lie C2 graded superalgebra of derivation of Guzman algebra. This is the principal aim, but in fact, we were working in that time with the observer algebras. Then the problem of algebra of observers was present in the idea of this presentation. Then the first steps is to make some basic definitions that maybe we can remember here. The first of them is the axiomatic approach to physics, and in particular to electromagnetics. Then we presented here the two physical laws of charge conservation and work conservation. And those were related with the differential forms of grade 2 and grade the dimension of space -1 for the charge conservation. And then this is the starting point, and the idea is to work with these two laws for will the observer dependent laws. Then all the work is directed in that way. Okay, this is the presentation of the two laws like described before. And here is the definition that we have discussed before of the observer field. Then the idea is to manipulate all of these operations using symbolic calculation. Then for this we need some definitions. This is for the definition of the space and time components of one multiform. And I think that this is important because it's the principal line of this presentation.
Could you, Jesus, could you skip back just a little bit? This notation E sub tau and E sub capital T. What are these?
Okay. And this, here it is in the split of the space. Wait a moment. Okay, here is in the split of the space, and then tau is related. Here it is the definition of the observer, and here is it is tau and it is t.
But when you wrote on the next slide E sub tau and
okay,
E sub t.
Maybe okay, here it is necessary go first to the next. No, I think excuse me, because it is defined here. Here it is E and I. Here is this definition. Then we are using here the creation and annihilation operators that when we use E sub tau, we are thinking in that it is in the module, and when we use E T, we are thinking in the dual of the module.
Yes.
Mm-hmm. Then this
But
is
it's based on this definition of E as an operator.
yes, yes.
And so when you write this binary
maybe
operator with the subscript, you're looking at the map, right? The map.
yes.
Okay.
Here you see the operation, the definition.
Mm-hmm. Yes.
Yeah, it goes both directions.
Mm-hmm. Then, okay, I go back.
Yes.
But this is the one of the more useful definition, because this can permit to us to define some algorithmic process for going in higher degree of the forms. Then I think that it is important, this. And for the split of the space and time components, those can be used. Here is the space component, and here is the time component of the differential form. Then the idea is that if we define in an axiomatic way the laws of electromagnetics, then we can split those for one observer. Here, K is a observer. Okay. Then this is part of the algorithm that we are going to use. Here we are rewriting the space and time components in terms of the Lie derivation. Okay. Then, okay, we can go now to the algorithm, and then I think that it is important, the idea behind this, because we are looking for a grammar definition of this of these objects, and then with that grammar definition, we are looking about the necessary transformation of that of those objects using some principal operations based on the definitions that I showed before. Okay, and okay, and the aims of this algorithm is to work with the Frolinger and Nijenko's bracket, and to build the observer algebra and the elements of Guzman multiplications and Jacobi identity. This is the principal aims of this this work. And okay, this is for the Guzman algebra. Then we start with these properties, the property of grade and the property of the Guzman product. And I think that this is the principal definitions that we can build in the Guzman algebra in symbolic calculations. Then I go to the
one question. Yes,
yeah.
you have here the grade of the wedge. Grade, the third item, grade of the wedge.
Is
The grade of
zero.
wedge is set to be equal to 0?
Yes, yes. Because in the Guzman product, the grade of the new form is only the addition of the grades of the two forms in the product.
I'm just not. I understand assigning a grade to alpha and to beta, but I'm not sure I understand assigning a grade to the Guzman multiplication.
Yeah, what does that grade wedge equal to 0 mean?
Yes, exactly.
Yes, I think that if we all of this
Well, that's a definition, I guess. Grade wedge is equal to 0 because it doesn't affect the grade alpha plus grade beta. So I think, yeah, I guess that's the whole idea.
and the same is for the plus sign, because if we take the grade in the, for example, grade of alpha plus beta, then this is equal to the higher degree of alpha or beta. This is equal to grade alpha if grade of alpha is higher
than grade B.
Then the operation grade is acting on all the elements of the expression.
Yeah, that's right. Most people don't look at that as being necessary even to talk, but I know Dr. Algebraic was very particular of what do you assign the grade of alpha wedge B? So the grade of the operator is 0. That's all he's saying. Or plus, the grade of it plus is equal to 0.
But the operator E sub alpha, for example, E sub alpha grade is
alpha.
Not 0.
No, excuse me, grade is grade of alpha.
Yeah.
Yes. Maybe it is. It looks like unnecessary to define here the grade of the operator, but after in the implementation of the calculation, it is necessary because here plus wedge and all the operators are in the same category of all the elements of the algebra. Then,
but the last two points on in your last point, you have that this E operator decreases the grade, right? And the I operator increases the grade.
yes, this is the, and then the grade of I operator can be defined like negative, with a negative grade.
Yeah. You're saying the grade of alpha plus beta is equal to the larger of the grades of alpha or beta. It's just a definition, really. That's all it is.
Yes, yeah. But the important thing is that it is necessary this the definition of this operation here in the Guzman algebra.
Yeah. So what's the grade of zero? What's the grade of zero?
Zero is an scalar.
So its grade is 0.
The grade of 0 is 0.
But the grade of, if you have that was a Dr. Page's question, that you have to have a different 0 for every grade.
Okay, you are right. And then, for example, in this operation, we need to read the grade of 0 here, like 2 times the grade of alpha.
Yeah, I think about grade of 0 is just 0. Well, that's, yeah. I identify my zeros of different grades.
Okay. And at the end, this was a point that I remember Professor Rosiewicz liked to discuss, because he insisted that the 0 here have not the same meaning that here, for example.
Yeah, grade, yeah, alpha.
I have one more question about the last two equations there. It seems maybe the arrows are in an unusual direction, right? Because I think of E as increasing the grade, but the arrow suggests that. So I mean, so E is like
Okay.
the left adjoint of the product, right? So E is like adding 1 to the grade, whereas I is like subtracting 1 from the grade. If you insert a vector into a form, right, then the insertion of the vector into the form decreases the grade of the form by 1.
Yes, it is necessary to change this to
plus and minus.
Here. Hmm?
Yes. Okay.
Yeah. And okay, if we maintain the arrow in the same direction to the right, then this is right. Mm-hmm. Okay.
Yes.
And I need to correct this. Yes. Okay.
All right.
Okay. Then.
Okay, that was a little confusing then. Yeah.
Yes. Mm-hmm. Okay. This is the same formulation, and okay. for the derivation operations, we need to a set of symbols that are the name, the grade, and I don't remember, this is, I think it is necessary for the property of the derivation, but it is necessary for the to add the Leibniz axiom. Okay, then I think that here in this set that I am putting is necessary to add the Leibniz axiom that is the definition of the axiom of the derivation operator. Okay, those are only general properties. And now we go to symbolic calculations. Then, since here I am speaking about some general characteristics of Mathematica, but I think that we can speak this in a more general way because we can define this calculation in a more abstract way. Then, okay, we start here. And one first important thing is that we have in the lower level some elements that are called the building blocks. And here there are the definitions. The idea is that from here, all the expressions are builded. And the idea is that we are going to build new elements only combining these building blocks. It is similar to idea of bricks in a building process. Then we start with this building blocks. Here I have a more extended idea that we have the internal data types that are built with the starting with the building blocks, but following a syntax for that. And the idea is that the expressions are used as values, but expressions are used for express the programs. Then here expression is a fundamental element in the definition of a program. Then the idea is that we are only building the expressions with the building blocks. And there are some special building blocks that are the basic data types. Those types of blocks cannot be reduced to a more fundamental form, because in this way they are called atoms. And examples of these are, for example, integers, reals, complex, or these sets of numbers. Then, if we start with these atomic types, we are going to build expression or compose expressions that at the same time are building blocks. Then, in the same, with those properties that we have, that are atoms and expressions, we are going to have different styles for displaying the expressions. And then we can have different kind of displaying these expressions, but at the end, these expressions are wielded with basic blocks, with the basic data types. Then this is in general the idea. Okay, and here is what have an atom. And an atom either have is built with expressions that have head and have an element that is the same atom. This is the principal expression that we are going to use with head and elements here. Those elements at the end are attributes for the object that has been wielded. This is similar to ideas that Professor Osievi used to use, because, for example, he used to define a set of objects. For example, this, maybe this, and this, and with those, it is possible to build or to define an algebra. Then the idea is that we have some atomic elements, and with those these atomic elements, we are it is possible to combine them for building some kind of expressions. For example, we can build something like this. Then we need to follow one rule of writing using these atoms with one syntax that are used for build more complex expression like this. Okay. Those are the principal atoms used in mathematics.
I suppose that's like knot theory that's possible with that notation.
Excuse me?
It looks to me like knot theory can be approached with that notation. The theory of knots, is quite complicated.
Oh, okay. Maybe it can be approached with this, but I think it is more complicated to.
The motivation for some of the symbols that Ushevich uses.
Now that last symbol was a cross of two lines.
Yeah, it's usually referred to as braids. Right? It's a subset of knot theory. Right?
Okay.
Yes. Okay, then we can. And here we start with the composition of expressions. Like I said, one expression have three principal elements. The head, that is the name of the expression. The elements that are the attributes of the expressions, and the length that are the numbers of attributes that we have. Then with those elements, then all that we need to do is to build different kind of expressions using those atomic expressions that we defined before, and then build a new kind of expressions following rulers that are, in the case of Mathematica, only to define new expressions with this with those properties, head, elements, and length. Okay. Then when we build an expression, then the next problem is to analyze the expression. It is a kind of debugging process, because we need to find the different parts of the expressions, and then maybe we can make transformation of those that part of the expression. Mm-hmm. Then we have the head for analyze the head. There is a head functions. For example, if I have one expression, then I use the function head and apply to that expression. Then these functions can give to us the name of that expression. Mm-hmm. But we sometimes the head of expressions can be too much complex, and then when we get the head of the expression, we can again apply the head functions and extract to a lower level the head of that object, and we can go in this way until we get atomic expressions. This is maybe like a process of decomposition of that expression in all the parts, but in one hierarchical way. when we are working with expression, maybe it is important to extract some parts of the expressions, and then there is functions that can help to us to extract some part of a expression. For example, I need to get the n element of that expression. That is to extract the n argument of the original expression. Okay. Sometimes the functions are expressed in operator forms. But it is important that all the expression either have this structure. And if we have one expression in operator form, then we can obtain the corresponding standard expressions using another function that here in Mathematica is the full form. Then if it is used in this way. If we can obtain the full form of expressions, that this can show to us all the hierarchical structure that we are using for perform this calculation. There is more function used here that is, I not remember, I think that the name is tree. Then the function tree can show to us the decomposition of the expressions, but this can show to us how the parts of the operations are performed in this expression. Then for analyzing expression, those are the important functions here. And it is an important thing. The idea is that in Mathematica, everything is an expression, and then an assignment, statement, or a function definition of a rewriting rule or a sequence of statements, all of them are expressions. And then it's I think that it is similar to sequence of instructions that are performed in the when we are finding when we find this expression. Then we need only to build a sequence of expressions, and then with this we get a program. Here it is defining for programs. One program is have two important components: a pattern matching and a term rewriting. Then a program is a task of transformation of expressions. This is the idea. Then we can debug an expressions and look for a pattern, and then I localize this pattern, then I can rewrite that patterns, substitute this with a new expression. And then this is the general idea with this program. I think that it is the general ideas of the symbolic calculations, but I am going to show to you some implementation of this.
It's sometimes I like to distinguish this approach, which, as you said, is a symbolic calculation, from what I was talking about 2 weeks ago, where the objects have more direct relationship to the algebra. Here, the symbolic operations are just grammatical. They don't necessarily represent the mathematics unless you design these rewriting rules carefully to respect the mathematics.
But the idea is that in symbolic calculation, maybe I am going to put to stop here, and I am going to use the blackboard here. I can't see the word. Okay, here it is. Whiteboard. The idea is this. First of all, if we need to define some kind of objects that are going to be used in the calculation, then those objects are defined in this way. For example, a name with some kind of arguments. For example, okay, I can use the same notation. When I define this, I am only defining a set. But after, I need to define some kinds of operations. For example, if we need to get one element of this, for example, this, I need functions that are defined in this way. For example, E2 is the two element of the expression name. Then I am going here only building new kinds of elements, but when I find some properties between these parts of the object, then I am defining some operations that can use to us, that can help to us to find some properties of this. But after if we define some kind of morphemes, for example, plus that acts in name, cross name, no? And this gives to us one new element of name. And then I can build some different kinds of operations. And in this way, I am going to build some properties of transformation of name that are at the end morphemes that are that I am defining in this in the defined category. Then I think that this way of building the symbolic calculation is using the most abstract way of looking about the objects of the category and transforming them using the morphemes of the that are defined in the category. And in this way, then we can use the, for example, the definition of operands. With the definition of operands, then the we have the building blocks of this that I put before. And I need a rule for building more complex objects. That then the rule is in this way. I am going to write from top to bottom and from left to right. No? This is the rule. And then I have one, I don't remember the word, because here is like in with the plants, one operation of
this is grafting.
The grafting of these two
like
elements.
It comes from yes, it comes from the notion of grafting plants, of connecting one stem of one plant to the branch of another plant.
Okay, thanks. Then we are going to build more complex objects, grafting those elements. But in the way that we can use this grafting operation, we need first to analyze the properties of each element. For example, this element is one-to-one operations, and this is 1-to-2, and so this is 2-to-1, and this is only a switch. Then I have an operation 2-to-2. Because in the grafting operation, we need to decide, for example, if in this example that I put okay, the first element go first in the upper level, and the second is going behind of this. And then I need that the output of this element is the same that the input of this. Then this is a way of building this kind of objects, and then we can get more complex expressions, and after I need a transformation rule that are the morphisms of this. I need maybe more complex operations, but maybe if I have here, I can say that this is equivalent to this, for example.
Mm-hmm.
And then
an axiom.
This is an axiom. Then I am going to define some kind of some axioms that at the same time is the rule of rewriting this expression, because if in the expression I find this pattern, then I can replace with this. Mm-hmm. Then I think that the general ideas used in the mathematical programming language are enough, general enough for use it in a more abstract way.
Mm-hmm. One question is that like what you write is an axiom, so it's like an equation. It holds in both directions, but a rewriting rule is applied in only one direction. So you must, for example, decide that the right-hand side is simpler than the left-hand side, and so we convert this equation into a rewriting rule that reduces the complexity in some sense, right? We need to have some kind of measure that says that the left side is more complex and the right side is simpler. So this is how we apply this rule in that direction. Right?
Yes, but this is made when I define the program. Because in the algorithm, I am going to include one instructions that say that this must be replaced with this. Then I think you're right. These relations, this axiom, have two sides. But in the algorithms, I define how this axiom is applied.
And there is a potential problem if you have conflicting axioms, axioms that the order in which you apply the axioms is possible to create a situation where there is no simple move without first of all in order, like you have only local minima as opposed to global minima. So if you have these rules applied, you might end up in a local minimum. And the only way to get to the global minimum is to make the expression more complicated first, and then to apply it in a different order to this is
Yes,
there's a word for this. It's called the Church-Rosier property, right? If
yes,
certain sets of axioms have this property, and other sets of axioms might not have this property. And if I remember correctly, deciding whether a set of axioms satisfies this criteria is not so easy, right? Is not so simple. But
yes. But I think that this is the problem of writing a program.
to solve this problem, right?
Yes, to solve this kind of problems. Maybe one intermediate step is to define some theorems. And if I define, if I can show some theorems, then after I can use that those theorems for simplify some kind of expressions. Then I think that is the way that we can build that. And okay, those are the general ideas that I used for the implementation in this paper. I am going to share only to show to you some kind of calculation that I made that time. It's interesting that this can work. Okay. For example, here I not need in this expression the first that is you can see in the first row are not necessary yet because in the past it was needed to include some special package for perform some kinds of operations. But here the idea is that with this definition that I am doing, I am defining some kind of operations that after are represented in a graphical way, and then those are used with the union operators in the way of getting some more complex expressions. Then, for example, here we are only presenting some kind of operators, excuse me, some kind of expressions. And here we are now using those for show some properties. For example, if we use the operator derivation, this can be applied in the after we get the addition of two functions, or this can be applied getting first the derivation of these two functions and after adding them. Then here is where we are defining some properties of these operations that we are using.
So this property is at least one part of the linearity, right, of the different.
Yes, for the derivation. Yeah, and here I don't remember what was the purpose of this derivation. Okay. Here is the, excuse me. Okay, here is the operations with the Guzman product, but
on the right side you have the co-product, right? You have
yes, here in the upper level we have first co-product, and after we apply derivations and switch two of the created functions, and okay, and after we use the Guzman product for build. Okay, yes, this is the Leibniz. This is the Leibniz ruler that we are using here.
It's interesting that you have this co-product in. Yeah.
So it represents all types of products you can define in terms of a Guzman algebra and its co-algebra. It looks like what we're getting at.
Because Leibniz property implies a coproduct. And
so this is a Leibniz property we're looking at right now?
Yes, this is a Leibniz property. I think that in the paper that I sent to you, this the same. I think that in the paper here I the images are with some notations. Okay, here. Okay, here we have.
So what's the most complicated expression that you've worked out for a pictorial representation of a complicated expression?
But Professor, at the end, this was not too much difficult because the graphic expressions can be manipulated like expressions in general. And then those was that we used the union operations that can be used in a graphic calculation. It is interesting because then the graphics objects are manipulated like ordinary expressions. Then you can get without too much difficult this kind of expressions.
Yeah, okay. So I guess that figure 2 shows that the two sides are equivalent. All you have to do is what? Bend the other one around the other or something. Well, that's interesting.
That here is in the definition of axioms, we can take this only in that way, like an axiom that, but after those are going to be used in the definition of a program. Then this is the idea in general. I don't know, maybe there is some, no, okay. Here are some calculations with the Guzman product. The bold lines here are the input in the program, the expression input, and the expressions that are in the bottom are the output of one of each that I write it first.
So you have a picture of what you just showed now. You can write that as a picture, then demonstrate the same idea with a picture, I suppose.
Here, this is included in the document, but in this program, this is the mathematical presentation for use in an iPad. Then this only can reproduce the calculations that were defined before, but not here. I cannot make new calculations, but I can reproduce the calculation that was included here. I not remember what is the name of this program, but is for mathematical presentation of notebooks.
Interesting.
Okay, here welcome. Welcome to Wolfram Player. Is the Wolfram Player. And then we can use the Wolfram Cloud and to port interactive examples. Okay, there are some. Okay. Then this is the principal.
For the observer algebra, you have a program that can.
Yes, but observer. I think it is, but not too much, because I only made a substitution of the field elements that were getting after of the product of observers. Then the problem was to find the minimal polynomial of these operations, and okay, this is a short example, but I have in my computer more complex example than this. I think that I need to review this because here there are some strange symbols that are not part of the calculations. But here only that we that was made was to find the matrix form of the operators of the representation of observers, and then obtain the eigenvalues of the
Yes,
of
so you
this.
could diagonalize this
Yes,
matrix.
this is only the idea.
Yeah.
And
It was mentioned at the end of that paper that I referred to.
yes, I do not remember if I have some calculations here at the end. I think that here not yet. Derivation of linear exterior derivation. No, not yet. Here only I define one element of the observer, one property of the observer algebra, but not made any kind of calculation yet.
Okay.
Okay. But,
It's interesting.
Yeah.
This graphical calculus is an important idea, I think, but you're demonstrating in this worksheets that the graphical calculus is not a new idea in the sense that it's just another representation of symbolic manipulation that it's but the graphical calculus has advantage for a human to understand the intention or the meaning of the diagram. It's much easier to understand the meaning of the Leibniz. Well, maybe Leibniz is not so good an example, but there are other examples where it's easier to understand the meaning of the grafting, but somewhat more difficult to understand the actual symbolic expressions directly. So the idea of the graphical calculus, I think, was mostly to help the human being, the person to understand the correct operations to apply. Because there, in the symbolic calculations, there are many different rewriting rules that are possible, and the computer might be able to just explore all the possible rewriting rules until it finds some solution. But for a human being, that's too complicated, too time consuming to explore all options. But instead, with the graphical calculus, you can go more directly to the
Yeah, maybe
intended
you can
result.
apply it to analyzing pictures, artificial intelligence, some type of graphical system for analyzing, recognizing pattern recognition, whatever.
Well, in
But
the
of course,
case of
it's much more
Frobenius
complicated.
algebras, the case of Frobenius algebras is interesting because there is a lot you can say about the structure of the algebra if you know that it satisfies Frobenius axioms. Right? And the Frobenius axioms can be expressed in this graphical form. And in the programs that I was trying to demonstrate 2 weeks ago, this same graphical form is used to write the linear operators, to write the composition of linear operators, which if you were to write those operators in a traditional tensor notation with subscripted and superscripted symbols, the meaning of those expressions is obscure. But the meaning of the graphical diagrams is much easier to appreciate, to understand.
Yeah.
Very interesting.
Yes, I remember that Professor either likes to write a paper without words, only
Yes.
with
With just graphics, sometimes these are referred to as string diagrams, or sometimes process diagrams. And there is a physicist named Bob Koch from I think he's from Oxford, I think. He does quantum mechanics entirely in the most abstract way possible, using these string diagrams to represent the structure of the categories in a completely abstract way. It's intriguing, but it unfortunately it seems that it hasn't advanced very much. It's a interesting tool, but so far it's not convincing. I'm not sure quite like what one should expect. That it's interesting to have a language that is two-dimensional language instead of a linear language. So you think there should be some advantage to having this two-dimensional language. It gives you some more powerful language in which to express the mathematics, instead of just the usual presentation, which is essentially linear. It's just like sequentially writing one symbol after another, and even the rewriting rules are such that they are always just sort of reorganizing linear strings of things. So for the computer, rewriting linear strings of things is quite natural as far as the programming is concerned. But when it comes to understanding the mathematics, it's not so clear. Right? So the two-dimensional languages of these string diagrams is closer to the mathematics, I think. It's closer to the algebra.
Go from the mathematics to the symbolic representation of it, but it's not so easy to go from the symbolic representation back to the mathematics, it appears to me. I never recognized Leibniz in that figure.
Yes, yeah, it's but it tells you something about when you look at that graph and you say, oh yeah, I understand that this is Leibniz, but then you understand that it seems strange at first that Leibniz should require the coproduct structure, that it isn't obvious, right, that Leibniz has anything to do with the coalgebra. Right? But that way of writing the axiom should be an indication that the mathematics of the Leibniz axiom is more profound than you might think. It's deeper, right?
Yes, because
The usual.
in this can help to you to find new properties of these operations.
Yes,
Then,
but it's a help for the human, right? For the human being, not so much a help for the computer, since the computer can deal with these linear operations very efficiently. But to understand that these linear operations actually represent the mathematics is a hard problem. I think.
no.
So when I look at the Mathematica program and I think, well, how does this represent Grassmann algebra? It's it's not so simple, right? Whereas if I look at the axioms of Grassmann algebra written in a graphical form, then I can see almost immediately that this is Grassmann algebra. And then what you provided is the rules that say, if I have it in this form, then I can automatically produce the linear form that's needed by the computer. Okay. Well, maybe we should decide that in 2 weeks' time. Is it possible, Dr. Subject, for you to present something
Okay, yeah, that's fine.
in 2 weeks?
Yeah, I think I'll have done what I want to do with it in the simplest cases. I think might convince you more that nilpotents are really the basis building blocks for matrix algebras and more structures even than that. But
I'm interested to see what you mentioned about the possibility of using, say, 3 nilpotents instead of just 2 nilpotents, because I think that suggests that maybe besides duality, there is something like triality, or there's
well, that's what I'm actually looking at. In fact, I think there might be a very close relationship to space-time, the Dirac algebra, and 3 mutually compatible nilpotents. And pretty interesting what I'm looking at now.
So what you're suggesting is kind of going beyond duality. Duality is just dealing with 2 things, right?
That's right. That simple relation, AB plus BA equals 1. Well, suppose you have 3 nilpotents that satisfy the same type of relationship. What do you get?
Yeah.
Well, so it's difficult
from the point of view of physics.
More.
But from the point of view of physics, duality is sufficient for space and time, right? So duality is what we needed in order to define an observer, for example, in relativity. But maybe there is something in physics that is relevant to triality, right? I mean, we see it in particle physics that there are algebraic structures which go beyond just dual, beyond just being plus or minus. So in the nucleus of the atom, we have quarks, right, that have 3 different states. So in order to understand the algebraic structure of the nucleus of the atom, we need to go beyond the duality in some sense.
Yeah, so yeah, I think I'll be able to do something of interest in a couple of weeks about this.
Okay, great. I think that would be very interesting indeed.
Okay.
Well, it was very interesting talk with Dr. Cruz gave today too about this graphical structure of covectors and vectors, differential forms, coforms.
No. Okay. I think that this language can be extended to other problems, but when I reviewed my programs in Mathematica for this presentation, I was surprised that those are working now. Then maybe those can be used to extend the kind of operations that we can represent it here.
Yeah, that's right. Maybe you can show the structure of these nilpotents that I'm going to be talking about with a graphical picture. It shouldn't be that difficult. My rules are much simpler than the different rules that you're using for your graphical representations.
Okay. Mm-hmm.
Jesus, in your case, the duality comes from this binary operation, right? That you have a binary operation and you take its left part and then take its right part, right? So you can split this binary operation into two dual concepts. So, but if you have instead of a binary operation, if you have a trinary operation, then of course you have much more complicated range of possibilities that you can split out three separate things. That's one way, or you can split off just one and then you have a binary thing left, right? So with like this, instead of duality, if you have triality, it seems to me that this triality would be a much more complicated thing. You would have much more algebraic property, many more algebraic properties. And so I'm interested to see what Dr. Sobchak presents, as the range of possibilities, I guess. Like,
yeah. But I think that, for example, in the three-body problem, you have one interaction between three objects that are related between them. And there is, when I was presenting the idea of interactions, one of my ideas was to define extended properties, extensive properties. And these extensive properties represents the property of two of them. And then at the end, we go back to the dual interaction. But if we take the problem of quarks, for example, that you say, then there is a big problem because we cannot separate one quark. And then it is not possible to define interaction between two quarks and the third, but only the properties of the particle is defined by the three quarks. And then in this case, I think that the problem of triality is fundamental. But I think that it can be, it needs to be understood because, for example, in category theory, we have only duality, but not have another more complex. I don't know if the old work that graph of graph or multigraph of multigraph that was been making with Professor Siewik, maybe this concept of triality can be defined because there the objects are more complex, are done more complex, and then we can define some kind of properties between those objects. Then it is too much interesting, your suggestion, and then I think that we can explore that in the way we can understand better this problem.
Yes.
This here is Ernesto's book. He has a section of his book on triality. I'm wondering whether we're talking about the same triality that Ernesto was talking about. You can see the title, the picture of it. I'm not sure
It's
that.
difficult for me to see, but
Yeah,
Yes, it is out of focus.
yeah.
yeah,
Well, anyway, I might take a picture or something and
sure.
look at it later.
Okay. Well,
Triality is an interesting concept. That very complicated expression that Ernesto goes through was one of the victories or that Ernesto had in writing his book on algebras and spinners. At the end of the book, he talks about the concept of triality, but of course there might be more than one concept, might not be related to what we're talking about.
Okay. It was a very interesting presentation today. Thank you very much. And I look forward to meeting again in 2 weeks.
I guess it can be a time change. It might be a time change in Mexico, I guess. Is that correct?
Yes. Yeah, it is correct.
Yes.
But remember that the Professor Page put the time for the conference in the standard time.
It's the
Universe,
absolute.
no? Absolute.
As the
Then,
UTC or Greenwich Mean Time. So it means that the apparent time, the local time of our meeting might be different, but the actual absolute time of our meeting will be the same, right?
yes.
So if you have a time change where you are located, then you would have to adjust the time of the conference of our meeting, right? But
Yes.
if you do not have any local change, then it remains the same for you.
I think that for the next 2 weeks, we are going to have the meeting at 10 o'clock in the morning in time of Mexico City.
Instead of
Oh,
the
okay.
11.
That's 2 hours difference. If I'm not sure when we change times in South Carolina.
So,
I'll check.
if you have to adjust your clock, then you also have to adjust the time of our meeting to compensate, right? Because the time
just
of the
ask
meeting
Google.
doesn't
Google
change.
keeps it straight.
Yes, exactly. Anyway, if you're concerned, I can send a notice or something in 10 days or so just to remind you that it might be different.
Yes.
Okay. Okay, thank you very much, and we'll see you again in 2 weeks.
Okay.
Enjoy.
Here is
Yeah,
my
bye.
Bye-bye.
bye.